is that we like to discuss the two quantities on the resolving power of the grating, and while calculations of the resolving power, we can use one relations that is called the Rayleigh's criterion for limit of resolution. So these two are very important, that while calculating, you know, resolving power, this understanding this is very important, because I already told that whenever you see any image, you basically see the diffraction pattern. So let us try to understand the resolution of the grating. Now, you see the Rayleigh's criterion for limit of resolution. Now, what do you mean by the resolution? For example, when you see an object in a microscope, what do you think about the resolution? So, what do you expect when you see a object in a microscope? Can you tell me that when you see any object in a microscope, what do you basically do and what do you expect? What do you want?
It will
So
zoom
a
into the object.
large,
Sir,
large
we
image of
want
the
a
object.
clear image, a distinguishable image.
Yeah, that means that you want to separate out two closely spaced points to a larger magnification, isn't it? So that you can
Yes,
see.
sir.
Yeah, like a object are very closely spaced, but you are not able to see. So you want them to be magnified and separated out. So that is the thing. And when you see in a telescope, what is the objective?
To
To
see the
view
long
a
object.
large distance object in a
Yeah,
distance.
yeah. So there are distant objects, but you want that those objects are coming close to each other, and you can see them clearly. So whatever the situation, that when you see the object, you want to separate them out clearly. That's one of the objective. Now, what is the problem there? Like if, for example, say, just imagine you are in a classroom, and I am just writing down in the blackboard. Particularly in the first semester, we have a big board on the room. So, for example, you are sitting in the hall, and let I'm putting 2 points which are widely separated. Now, all students, even in the student who are sitting in the last bench, they can also clearly see. Now, let I am bringing those points closer and closer and closer. Now, what will happen after some time? Maybe the student who is sitting in the first bench, they will be able to separate out, but the student who are sitting in the, say, in the towards the last side, last part of the room, they will be saying, oh, perhaps there is only 1 point on the board, isn't it? I think you can visualize it. Now, what is the problem? Actually, in reality, the image formed by the lens in microscope or telescope are not the point image basically. These are circular diffraction pattern formed by the limited portion of the wavefront transmitted by the lens system. If when we see in our necktie, we have also a lens in the eye. So our eye definitely does not collect all the light. We have an aperture in the eye, so we collect a part of the light coming from any object. Similarly, in the microscope, telescope, they collect a part of the light. So a telescope become costlier when you increase the size of the lens. Okay, the cost of the telescope depends on the size of your lens. One of the factors, definitely there are other factors, that is not the only. So if you make larger size, more light will be collected, so intensity will increase. And definitely there are other complexity to manage when you make a large size lens. Anyway, so that means whenever you use any viewing object, either the viewing detector, either your own necktie or use a microscope or a telescope, you are seeing not seeing the point objects, you are seeing the image of that, that is refraction pattern of that. So, and each diffraction pattern, for example, if you remember the single eclipse, say I am seeing a point, and basically we will see what? We will see this diffraction pattern. We will see this diffraction pattern. I see another point placed at point B, I see its diffraction pattern. Now, when these 2 points are very closely spaced, resultant we will see actually a resultant like this, that there are two peaks, and in between there is some minimum, and then so we feel that as if there are 2 points. Okay, like if you go to a hill stations and there are, say small hills close by, and from long distance you'll feel as if the two hills are very closely spaced. But when you come to the closer, you find they are widely separated. So when the 2 points are widely separated, we can see them distinctly. But as we brought them closer and closer, now these two diffraction band will overlap. These two diffraction band will overlap. So there is a criterion that Lord Rayleigh achieved, arrived at the conclusion after a detailed study that two equally bright point sources, say both the point sources are equally bright, would be just resolved by any optical system when their distance apart is such that the central maxima in the diffraction pattern due to one source, I repeat, the central maximum in the diffraction pattern due to one source coincided exactly with the first minimum in the diffraction pattern due to the other. Okay. Then these 2 point object will be clearly resolvable, and this is known as Rayleigh's criterion of resolution. So what it says, the central maxima, for example, the central maxima due to A is formed here. At the same location, the first minimum due to B has to be formed. So the first minimum of B has been formed here, or the first minimum of the A is formed at the location of the B. Then these two objects are clearly resolvable. We can separate out, but if B is even brought closer, then actually resultant will be like this. Okay, if we brought B further, then the resultant will be like this. The resultant will be like this. So we will not be able to recognize that there are two objects. So this criterion can be used to find the resolution of spectral lines of equal intensity formed by grating or prism. Even not only that, separating two objects in space, like if there are two wavelengths present, for example, in the sodium light, there are two yellow lines, 589.0 and 589.6 nanometers. In sodium, like if you heat up salt, you will find the yellow lights are coming out. Now, in general, in the normally you will see that there is only one wavelength, but if you send through a spectrograph, you can find that there are actually two different wavelengths separated by 0.6 nanometers. So such wavelengths, such spectral lines of equal intensity can be separated, or you can find out the resolution of spectral lines of equal intensity formed by grating or prism spectrograph. So in the same way, like there are two wavelengths, say one at lambda, another plus lambda plus d lambda. So for example, your incident light contains two wavelengths, one is at wavelength lambda, another at lambda plus d lambda. Now if the principal maxima of one formed at the minima due to the other, then these two wavelengths will be separated out. So the same criterion can be used to calculate the resolutions of the grating that we will be discussing. So let me elaborately discuss further. So Rayleigh's criterion of resolution can also be restated as the angular separation between the principal maxima of two spectral lines in a given order. So both are the same order, and their angular separation between the principal maxima of the two spectral lines in a given order should be equal to half angular width of either principal maxima. So this angular separation should be half angular width. Okay, the angular separation between the two principal maxima of the two spectral lines, for example, one at form at an angle theta. Say we have a grating here. Now one has been, say we have a grating here, and one has formed at an angle theta, and another has been formed at angle theta plus d theta. So the angular separation is d theta. Now this angular separation, if this angular separation is equal to the half angular width of either principal maxima, this is nearly half angular width of either maxima, roughly. Okay, so Rayleigh's criterion can also be described in this way. Now in symbols, the condition means that if the principal maximum of lambda is found by an optical instrument at an emergent angle theta, and the principal maximum of the same order of lambda plus d lambda is formed at theta plus d theta, then the first minimum in the diffraction pattern due to lambda should also be formed at an angle theta plus d theta. So as I was discussing, say there are two well separated peaks and there is no problem, and here the two peaks are clearly separated, still resolvable. Like this is far away, but here we brought them closer. The two wavelengths are a little closer, still resolvable. But again, if the two wavelengths are further, they closely separated, lambda and dash and lambda dash plus d lambda dash is very closely spaced, closely close wavelength, then the resultant will be like this, and we cannot resolve it. So we can understand the Rayleigh's criterion by these descriptions. Now let us calculate the resolving power of a grating by using this relation. So by the way, if you have any questions or the doubt about the Rayleigh's criterion, that can be discussed. So is it clear? So because you must make it clear, otherwise there will be problem with you. So is it okay? Is it understandable?
Yes, sir.
Yeah. Then let me progress. If you don't have any questions, then let me proceed. So the resolving power of a grating. Now let a plane wavefront of light consisting with lambda and lambda plus d lambda is incident on a grating normally. So there are two closely spaced wavelengths present and we incident in the grating and normal incidence. And the diffraction pattern is formed in the focal plane of a lens corresponds to lambda and lambda plus d lambda wavelength of the light. Now according to the Rayleigh's criterion, these two wavelengths can be resolved if the maximum for the lambda plus d lambda just coincide with the first minimum for lambda, as shown in earlier figure which I have reproduced here. So this we have already discussed. If the maximum for lambda plus d lambda just coincide with the first minimum for lambda. So at the same position, there should be first minimum for the lambda, where the nth order principal maxima has been formed for lambda plus d lambda. So the condition for nth order principal maxima for lambda plus d lambda is d sin theta n into lambda plus d lambda, isn't it? So this is the condition for the maximum for nth order. Now condition for the first minimum after the nth order for lambda, n lambda plus lambda by n. This all of you know. So the next minimum, that is n plus 1th minimum, will be formed at d sin theta, the same angle, and the condition for that, it has to be n lambda plus lambda by n. Now if you compare these two equations, by using these two equations you can calculate that the resolving power, that is defined as lambda by delta lambda. Okay. So the resolving power of a grating is defined as lambda by delta lambda, when the two light of two closely spaced wavelength of having wavelength lambda and lambda plus d lambda incident on a grating, then its resolving power is defined as lambda by d lambda, delta lambda. So if the smaller is the delta lambda, larger is the resolving power, and that is found to be n into n. So lambda by delta lambda is n, resolving power of the grating. Now we can substitute the value of n and capital N. So small n is e plus b sin theta by lambda, because e plus b sin theta n lambda. So we can substitute the value of n here, and then it becomes n into d sin theta by lambda, where d is e plus b, n into d sin theta by lambda. Now n into d, what is that? D is the spacing between two slits, the spacing between two consecutive slits, and there are total n number of slits. For example, you have a grating, and here there are total n number of slits, and two slits are separated by d, and there are n number of slits, and two slits separation is d. So the total width become n into d. So W is the total width of the ruled surface of the grating. So lambda by d lambda, sometimes written as W sin theta by lambda. So it depends on the total width of the ruled surface. It does not individually depend on n and d, like you can make n large and d small, or d large n small, so that the product n d is same. So the lambda by d lambda is dependent on that. Yeah, but here the condition is that you are shining the whole grating. The light should be shined on the whole grating, then the whole width is useful, otherwise whole width is not useful. So lambda by d lambda is W sin theta by lambda. Now we will use these equations, either lambda by d lambda is nn or lambda by d lambda W sin theta by lambda, to solve some problems. For example, here one problem is given. that calculate the least width that a grating must have to resolve two components of the sodium D lines in the first order. So I was telling you the sodium D lines, there are the two wavelengths, one is called the D1 and the D2, this is 589.0 nanometer and 589.6 nanometer. There are two wavelengths in the sodium. So you have to resolve, these two wavelengths. That means delta lambda has to be at least 0.6 nanometer. Then and you have to resolve in the first order, because you see this resolving power depends on the order number also. As you go to the higher order, the resolving power increase. So lambda by d lambda is proportional to n. So the resolving power will be larger in the higher order. And if you use more number of lines, then you can have a larger value of the resolving power. And more number of lines per unit length, you increase the cost of the grating, because you have to make more closely spaced wavelength and you need finer technology, so the cost also increased. Now anyway, it is given here in this problem that you have a grating of 800 lines per centimeter, and it is given that you want the lines of the sodium are these. And so to resolve to closed lines lambda lambda plus d lambda, we know that this condition has to be satisfied, that lambda by d lambda is an n, and here n is 1, so lambda by d lambda should be n. So n is equal to d lambda, lambda by d lambda. Here lambda we have to take the average between the two, so 589 plus 589.6 by 2, and d lambda is 0.6 nanometer. Both is nanometer units, so we have not converted, it is cancelled out. So ultimately we get n is equal to 982.2. So and then therefore the width of the grating has to be, it has 800 lines per centimeter, 800 lines per centimeter. This is not nanometer, I am sorry, there will be no unit here because this is a number. So I am sorry, this is a mistake. So 982.2 is the number of lines per unit length, and here it is 800 lines per unit length. So therefore the width of the grating has to be 982.2 by 800 into millimeter, so 10 has been multiplied, so 12.2 millimeters. So your width of the grating, minimum width of the grating has to be 12 millimeter. So these type of problems we will solve. Now if you have no questions, then I'll go to some problem set, or we'll review these two chapters. Almost it is done, only some problems again, as I give for the interference here also some problems I'll give you, and I can discuss quickly the solutions. Do you have any question by the way?